Hello everyone, my name is Kla Chakrit Tantitam Tawon. I am a senior lecturer in software engineering at Monash University. Today myself, together with my PhD student Shanatip Pronprasit, we are going to present the paper titled JITLine, a simpler, better, faster, finer-grained just-in-time defect prediction. Normally, large-scale software projects often receive a large number of newly arrived commits every day. According to Google-based software engineering practices, such commits need to be reviewed by other practitioners prior to integrating into the release branch. However, with the limited time and human resources, it is infeasible that practitioners can exhaustively review all commits. Thus, just-in-time defect prediction has been proposed to predict which commits are the most risky or are likely to be defective in the future. So, to build a JIT defect model, we first train a JIT model using a historical data of the characteristics of the defect-introducing commits in order to predict whether a newly arrived commit will introduce defects in the future or not, while the insights derived from the JIT defect models can also be used to better understand what factors are the most associated with defects in the past so we can avoid in the future. As everyone knows that each commit is still very large and complex, the size of the commits varies from 100 to 1000 lines of code, but not all lines of code in a commit is actually risky. Surprisingly, only 50% of them are actually important, so practitioners still don't know which lines are most risky. Since current predictions are not understandable by practitioners, it could just lead to a lack of adoption of JIT defect models in practice and poor SQA resource prioritization. To address this challenge, we propose JITLine, the first line-level defect prediction approach using expandable AI technique. The goal of this work is to help practitioners identify which lines are the most risky for a given commit, so practitioners can just inspect and focus on that lines instead of wasting their time reviewing the whole commit. To do so, we start from a training dataset. For each commit, we will convert the source code, the change lines, into a backup token features. So our feature vector will be the frequency of tokens that appear in that commit. Then we apply smooth with a hyperparameter optimization using a differential evolution approach. Then we build a commit level just-in-time defect prediction model using our pre-processed training dataset. For each commit in the testing dataset, we use LAM, a state-of-the-art model agnostic technique to explain the prediction. So with this approach, it allows us to understand which tokens contribute the most to the commit. Then we can compute which lines are the most defective. We set out to investigate 4 research questions. First, we ask, does our JITLine outperform the state-of-the-art JIT defect prediction approaches? We found that JITLine is 26% to 38% more accurate than the state-of-the-art approach. Second, we also ask, is our JITLine more cost-effective than the state-of-the-art approach? And what we found is that JITLine saves the amount of effort by 89% to 96% to find the same numbers of defect-introducing commits. The IQ3 we asked, is our JITLine faster than the state-of-the-art JIT defect prediction approaches or not? We found that JITLine actually takes 1 to 3 minutes by the CPU. Finally, we asked, how effective is our JITLine approach for prioritizing defective lines for a given defect-introducing commit? And we found that our approach is 133 and 150% more accurate in identifying defective lines than the Ngram approach by Yan et al. So these results lead us to conclude that JITLine may help practitioners better prioritize defect-introducing commits and better identify defective lines.